Hello everyone. Today we are going to talk about trigonometric integrals. And we're going to start with something very simple. I'm just going to kind of consider several examples which are going to help us to make substitution like easy when we deal with lots of trigonometric integrals. We're going to start with example number one. Example number one is going to be some kind of obvious example. Imagine that we'll need to integrate sine to the power of 5 x multiplied by cosine of x, then dx. So there is a mixture of sine and cosine, different powers. Here is power 1, power 5, and the argument is just x. Well, if you look carefully at this expression, kind of easy to guess. We have a composition which is sine to the power of 5. Makes sense to do a substitution. U equals what? Sine of x, right? Then du, derivative of sine is cosine of x, dx, right? And our integral is turning into u to the power of 5, right? Sine turns into u to the power of 5, and cosine dx is turning into just du. Very easy to calculate. Power function u to the power of 6 over 6. And if you go back to original variable, it's going to be sine to the power of 6 of x divided over 6 plus a constant. Kind of easy, right? So here, substitution was obvious because we've seen that argument of the composition was sine of x. But what should we do if we have something like this? Let's say cosine to the power of 5 of x dx. Well, the previous section, we learned that there is a reduction formula, right? Which is allowing to reduce the power of cosine by 2 units every time you apply it. Because the power is 5 here, we reduce it 2 units is going to be 3, and then one more application of the formula, a reduction by 2 more units is going to be 1, which we can integrate. Well, it's going to be a long solution, right? Reduction formula, first you will need to recall it. Second, you will need to use it 2 times. Do we have any easier solution? Actually, yes. Let's see how it's going to look if we apply a little trick. I'm going to separate one cosine of this 5 cosines into a separate factor. And I already know that cosine dx can be du if your u is a sine. The only bad thing here is that this one is not a sine, right? Same substitution can be used. This is du, but this is d sine. I'm going to write it down. There is something, and here is d sine. Well, to integrate in terms of sine, we'll need to convert cosine to the power of 4 into sine. Oh, we can do this. We can do this by using Pythagorean identity. Let me remind you, cosine square of x plus sine square of x equals to 1, which allows us to convert cosine square of x into 1 minus sine square of x, right? So whenever you deal with each cosine square can be converted into 1 minus sine. How many cosine squares we have here? Well, 2 actually. Cosine square multiplied by cosine square. So what I'm going to do, I'm going to write it 1 minus sine square of x squared, right? Because like 4 power of 4, it's a cosine square squared. And now everything is in terms of one variable, which is kind of u. And I'm going to write down 1 minus u squared squared u. We can integrate it. It's just a polynomial. I'm going to quickly open this parenthesis and do the integration. So I have 1, right? 1 square minus 2 u square, 2 by 1 by u square, and plus u to the power of 4 du. And the integral is going to be u minus 2 u cubed over 3, because power is 2 plus 1 is 3, right? Plus u to the power of 5 over 5. And I'll need to go back to original variable, which was what? Sine. So I'm going to plug in sine of x here, minus 2 sine cube of x here over 3, and plus sine to the power of 5 of x over 5 plus a constant. That's the final answer. What is the difference between example 1 and example 2? In example 1, substitution was obvious by looking at like composition, right? Composition is a sine to the power of 5, so we look at the argument of this composition is sine, so we do substitution of sine. Here, substitution is totally not obvious, right? Though the whole function is about cosine, we do substitution of sine because we actually can convert the remaining cosine to the sine. And that's going to be a key concept for this trigonometric integrals section. So whenever we have product of several trigonometric functions and we are planning to do a substitution, we'll need to make sure that we convert the rest of like trigonometry to the same variable. And our best friend is going to be Pythagorean identity. The bad thing about Pythagorean identity, it converts only squares. For example, if you have a cosine square, it's going to become 1 minus sine square. If you have a sine square, it's going to become 1 minus cosine square. Yeah. If you want to convert the first power of cosine, you are going to get a square root here. And for the square root, we really don't know what is going to be the integral. So it's good for us like when we convert the cosine, but when we just convert squares, we have polynomial. If we convert square roots, we are going to get square roots. So the idea is to make sure that when we do a substitution, the remaining function can be converted to whatever variable is. Let me consider next example. Scroll this example up. And there's going to be my next example. Example number 3. Let's consider sine to the power of 5 of x cosine square of x dx. What should be our substitution in this case? You see that we have a product of sine and cosine, and one is to the power of 5, one is a square. Well, usually, like for the first like 2, 3 examples, you probably won't be sure what substitution to do. And you are always kind of free to do substitution like either sine or cosine and see where we go. Usually, if you do correct substitution, everything is going to work and click and you are going to get the final answer easily. If you do wrong substitution, you are going to end up with a square root eventually, and square root is going to tell you, yeah, substitution is wrong. So here, guys, what I'm going to do, I see that I have sine to the power of 5. I know that if I choose substitution of cosine, this cosine easily is going to become u. But for this one, I'll need to convert it to cosine, right? And I can convert only 4 sines to cosine because that's square of square. So there's going to be one remaining sine. For us, it's actually good because when we do substitution, there is supposed to be d sine or d cosine over here. So we supposed to use either one of these like sines to become a d cosine. So why don't we try it? So use substitution, u equals cosine of x. There's going to be du. Du is going to be sine of x dx. And that's going to be with minus because derivative of cosine is negative sine, right? So what we have left, yes, what I'm going to do, I'm going to just write down four of these sines. And then the cosine square. And then write down sine of x dx. So I know that this one is going to become my du. Well, because cosine is my new variable, I'm going to have over here u squared. What should I do with this? Well, like I did over here with cosine, I'll need to represent sine through cosine, right? And using Pythagorean identity, it's going to be 1 minus cosine square of x, and that's going to be sine squared. Because we have sine to the power of 4, we'll need to square it. And that's how my expression is going to look, except instead of cosine square, I'm supposed to use u squared. Let's write it down in one line and integrate. 1 minus u squared and then u squared, and then du. And we just need to multiply everything. Well, again, we open parentheses. 1 minus 2u squared plus u to the power of 4, u squared du, and then multiply everything, opening parentheses. U squared minus 2u to the power of 4 plus u to the power of 6. And du, yes, I'm just going to integrate and substitute cosine back in one line, just not waste more time. So we're supposed to get u squared is going to give us u cubed. Our u is cosine, so it's cosine cubed over 3 minus 2 cosine to the power of 5 over 5, right? The power increases by 1 unit. And plus cosine to the power of 7 over 7 and plus a constant. So that's how we did the integral. Now time to kind of point interesting stuff on this integral. If you look at this integral, you see that it was necessary to have sine over here odd because we use one of these signs to make du, right? And all other signs must make even power to be converted to cosine. But it was not important what is the power of cosine because cosine will be converted into u directly. So whether it's even or odd doesn't matter actually because it's just going to become either u square, u cube, or like whatever u. So I'm going to write down not important. Sorry, hard to write down this word. So, well, guys, if you have good visual memory, you can just try to memorize that if sine is odd, then your substitution is going to be cosine. Kind of strange, opposite, right? You look for the odd power. Which one is odd, sine or cosine? And then use opposite function to be your substitution. Cosine will be not important, like odd or even. Okay? So maybe I'll ask you to calculate something on your own. I'm going to write down a self problem over here. And I'm not going to solve it, we'll consider it in class. I'll give something similar, but the odd power is not going to be sine anymore. It's going to be cosine cube of x by sine square of x dx. Let me check if we did not solve this problem already now. Good. So that's going to be the problem to prepare for Wednesday. And one more problem. Cosine cube of x by sine cube of x. So according to my rule, you probably can assume that if odd power is not of sine but of cosine, then we are going to use substitution sign, right? So here in parentheses, I'm going to put your substitution actually, sine of x. But what substitution is supposed to use if both powers are odd? This is going to be the question, and you probably can guess. Try to use either sine or cosine, see how it's going to work. Okay. Okay, so we know how to deal with odd powers. So if you do have a product of sine and cosine, and one of the powers is odd, or both powers are odd, you know what to do substitution. But what should we do if we have product and both powers are even? For example, square and square, or fourth and fourth, or no, just two even powers. How should we work with that expression? Well, that was example number 3. Example number 4. Example number 4. Imagine that we have cosine square of x by sine of x dx. How shall we consider expression, or what kind of substitution we can do when we have both even powers? Well, first, let's try to do substitution u equals cosine of x. Just see how everything will go. If we substitute u equals cosine of x, the cosine is becoming u right away. From sine, we are going to borrow 1 to make du, and there's going to be 1 left, which is not good for us because we'll need to use Pythagorean identity and we'll get a square root. So this substitution doesn't work. Let's try sine substitution. If we do sine substitution, then sine is becoming easily u, but cosine will need to take one of them to make a derivative of sine and make du, and there's going to be 1 left over, which is not good again, square root for Pythagorean identity. So this one is not going to work either. What should we do? Well, guys, we'll need to modify this expression before we can integrate it. And I'm going to use double angle formulas. And you guys probably remember, I'm going to write down these formulas over here, somewhere in trigonometry, we were studying formulas of cosine of 2x, and it equals cosine of x squared plus, oh, sorry, plus minus sine square of x, like Pythagorean identity, right? And the sine of 2x equals 2 sine of x, cosine of x. These are called double angle formulas. They are very good formulas to review and to remember. So if you have argument with double angle, you can convert it to squares of singular angle. For this integral, we are just going to use formula number 1 and Pythagorean identity. Watch how I'm going to do it. I'm going to obtain it once, and then I'm going to assume that you guys know that, okay? And then we are going to calculate the integral. So we change the color. So here, guys, I have cosine of 2x equals cosine square of x minus sine square of x. What I'm going to do, guys, I'm going to substitute instead of cosine 1 minus sine square of x. And this is Pythagorean identity, right? 1 minus sine square of x is a cosine. So if I continue expression, I'm going to get 1. There is one sign and another sign, both with minuses. Now I have cosine of 2x equals, I'm going to copy it, equals 1 minus 2 sine of x. What I'm going to do next, I'm going to move sine to the left side, cosine to the right side, and divide by 2. So I'm going to have sine of x, and here 1 minus cosine of 2x. And if I divide by 2 both sides, this 2 cancels, and this 2 is going to just give me 2. That's going to be formula number 1, which is going to convert kind of half angle to double angle, or like singular angle to double angle. Why it's good? Because it converts square into a lower power. And usually, guys, lower is power of cosine or sine, easier it's going to be integrated. So, but that's not just the one formula we need. I'm going to circle this formula and get another formula for cosine. We are going to get a very similar formula for cosine. Now, if instead of cosine square, I represent using Pythagorean identity sine square, I'm going to get my second formula. X equals cosine. I'm going to copy cosine, but instead of sine, I'm going to write down 1 minus cosine square of x. Again, I'm using Pythagorean identity here. So sine square is equal to 1 minus cosine. Here, if I simplify it, I'm going to get 2 cosine square of x minus 1. And I'm going to, in this case, I'm going to move this 1 over here, and I'm going to have cosine of 2x minus 1 and divide by 2. Get cosine square of x. And that's going to be my second formula. Yeah, looks like it's totally different formula, but if you compare these two formulas, you're going to see sine square, cosine square. 1 minus cosine. Sorry, I'm supposed to put plus over here. When I was moving this 1, it's supposed to be plus 1 plus cosine divided over 2 divided over 2. So what I'm going to do, guys, I'm going to use these both formulas to change these powers into something smaller. Instead of cosine square, I'm going to write out 1 plus cosine of 2x over 2. Instead of sine square, I'm going to write down 1 minus cosine of 2x over 2. So cosine has plus, sine has minus. And simplify it now a little bit. So what I have, I'm going to put 1 over 4 in front of the integral, combining these two denominators, right? And I have a plus b, a minus b, which is going to be a square minus b square, the formula, right? So I have 1 minus cosine square of 2x dx. So what should I do next? I still kind of don't, well, I can use reduction formula, but you remember, you're supposed to know formula, remember to use it. So I'm not going to do it. I'll try to use actually this double angle formula one more time. Because I have a square, cosine square, right? I can convert it into the first power of cosine. That's what I'm going to do. I'm going to write down 1 over 4. 1 cannot be converted to anything, so I'm going to just leave it. And instead of cosine square, I'm going to write down 1 plus cosine. My angle is 2x here. If I double it, it's already like not x, but 2x. If I double it, I'm going to get 4x. And divide over 2 dx, don't forget. And now I can simplify it a little bit. 1 over 4, and I have 1. If I divide by these 2, it's going to be minus 1/2, and then minus cosine of 4x over 2 dx. Now, guys, I'm ready to calculate the integral because I reduced everything to basically just simple cosine and a couple of constants, right? So, maybe I'm just going to integrate, 1 minus 1/2 is going to be what? Just 1/2, right? Integral of 1/2, it's 1 over 2. Here, guys, what we have. Minus 1 over 2. I'm copying this minus and this 2. What is integral of cosine? That's a sine, right? But if I differentiate sine of 4x, if I differentiate sine of 4x, I'm going to get cosine of 4x. And then when I differentiate 4x, I'm going to get extra 4 here. But actually, I kind of don't have it over here. So I'm going to divide by this extra 4. Formally, I'm supposed to use substitution here. 4x, use substitution u, then du, but it just like takes so much time. It's kind of obvious. You differentiate sine of 4x, you're going to get cosine of 4x by 4. 4 cancels, you're going to just get cosine of 4x. And this minus and this 2 are already here. Well, basically, guys, we are done. We just need to simplify this expression as much as possible. That's going to be it. 1 over 4 and 1 over 2 is going to give me 1 over 8x. 1 over 4, 1 over 2, and 1 over 4 is going to give me 1 over, I guess, 32, right? Sine of 4x. Don't forget a constant. I think I did not do any mistakes, but you guys, if you see any mistakes, unfortunately, I don't have a class to check my work, so just let me know if I kind of did any mistakes here. Okay, so I think what I'm going to do, guys, I'm going to give you one problem to work by yourself, and this even powers problems are very long, and there are not too many of them. So I'm going to give you one problem for self-work. Self-work. Integrate cosine to the power of 4 of x by sine square of x dx. Guys, maybe I'll give you one more problem because eventually I'll need to know how to do it. So how about this? Here, guys, I don't want you to use any reduction formulas. I want you to use substitution, and the substitution which I will just teach you. And here, for example, in the first problem, I will need to reduce first the powers of sine and cosine using the formulas for like a square of cosine and doubling the formulas. And here, also a good idea to reduce the power first and then integrate. Okay? Guys, I want to split this section into two parts because if I teach everything into one part, it's going to be really, really long video. So I'm going to stop at this point, and there are just like two problems here for self-work, and there is like, let me show you also. There are two problems here for self-work. Let me label them. It's just going to be a little bit easier. It's 1, 2, 3, and 4. Of course, you will need to practice in all homework problems too. Okay, so let's finish this one and kind of make other one separate video.